Hello everyone. So the next module is all about mass energy relations. So this will be talking about nuclear binding energy and how we would be applying them to the different nuclear reactions. So before we go to problem solving, let's first have some definitions. So when you talk about mass energy relations, of course we start with energy and mass. So when a system gains or loses energy, it also gains or loses a quantity of mass. Uh, that is actually a concept that we have to be familiar with. So the equation for energy is equal to mc squared, wherein delta m is the mass defect and delta E is the change in energy. You can actually rewrite the formula this way. You can say that delta E is equal to delta m c squared. Okay, it's the same as this one, granting that you'll be seeing in the problem changes in, so you have to use the deltas. Otherwise, you can use the formula by directly substituting the values of m and c without using the deltas or the changes in the values. If delta is negative, it means that mass is lost from the system, and that is what you call your exothermic uh, reaction, or it's called exothermic, meaning heat is being released from the system or mass is lost from the system. Okay, we take a look at that also. So this is exothermic, wherein mass is lost from the system. The next part would be, of course, the formula. If we go back, I already wrote it in this initial slide, but again, you can always rewrite the formula equals mc squared to delta E equals e squared delta m, or delta m times e squared. So it doesn't matter the order of the variables. Wherein delta m is called the mass defect, wherein, of course, since it's a delta, that will be mass of the products minus the mass of the reactants. In the equation, we know that the left side of the equation will be the reactant and the right side will be the product. Delta E would be the energy of the products minus the energy of the reactants, and C will be the speed of light. So how do you compute for mass defect? So for example, we have helium 42. Okay? Since atomic masses include the masses of the electrons, we must take into account for electron mass. So mass of an He42 atom is equal to the mass of helium-42 nucleus plus, of course, the mass of the electrons. Also, for example, we're using a hydrogen atom, hydrogen 1 atom. That should include the mass of the nucleus plus the mass of the electron. For example, in this case of helium-42, nucleus is synthesized from 2 protons and 2 neutrons. That's why, yes, you can see the mass number. The mass number is 4 since there are 2 protons and 2 neutrons. And then when we want to apply the formula of a product minus reactant, so that will be the mass of helium minus the mass of hydrogen in this case. And looking at the final value, that will be 0.0304. And where do you get those masses? So you also have, when you're doing mass energy relations computations, you should have a nuclear masses table, which is this one. So this is where you will be finding the masses. And um, take note that, for example, helium has helium-42 in this case. You also have helium-32, so their masses are different. Likewise, for hydrogen, for example, we have hydrogen 1 we have hydrogen 2 we have hydrogen 3 So you should follow which is directly related to what you are looking for. The different forms, for example, of hydrogen or helium, you take the masses that belongs to them. In this case, let's just see if this is aligned. If I can find a better table, I'll be uploading a better one. But for now, let's use this. For example, helium. Let's take helium 42, it means the mass is 4.00150. Let's validate that from the last um, example or sample. Yeah, it's 4.0026. Here it's 4.00150. So I guess, well, that could have been using a different table. Let's see for hydrogen 11. Hydrogen 11 is 1.00728. This is using the correct value. Probably later on, this is correct. Okay, probably later on we can use the real value or what we see in the actual table. I guess this is just an example, but this is supposed to be 4.0015. 4.00, yeah, that's 4.0015. We have to change that to 4.0015 if we will be using this table for the computation. Okay, because we're using helium 42. So it's helium 42, so it's supposed to be 4.0015 minus 2 ME minus 2. Okay, when you want to talk about the mass of the electron, then here in this case, it did not use 2 MEs anymore because this is 2 ME, and then that's 2 ME, and then but this is positive, positive. So I guess it got rid of that mathematically. So this is just to present the initial mass defect, how you will be computing for mass defect. But this has to be corrected later on, okay? So for now, let's just, it's already corrected, so I don't have my calculator with me. So just bear with me, we will just correct it later on for the problems that will be using it. Okay, for mass energy relations, since we'll be using the value of, you can see here c squared, and c is quite a big number. What we did was create a factor that can be used for c squared. So to obtain a more useful form of the equation, delta E equals c squared delta m, we substitute for c its value in meters per second because, yes, you can also see this in your calculators, where this is a very common constant that we are using in science and math. So speed of light is 3 times 10 to the 8 meters per second. So we already substitute that. We substitute that into the formula. So c squared, this is now c squared here. And then we convert 1 joule to 1 kilogram meter squared per second squared. And then we can get factors of delta E already. So we can say that this is one formula you can use for delta E, and this is another one. This one is in joules, if you've noticed, and the other one is in kilojoules. We'll be using that later on. So what is binding energy related to the topic? Because to be able to solve for binding energy, you should be able to get the mass defect. So binding energy is the energy required to decompose the nucleus into its components. For example, iron 56 is the most stable nucleus and has a binding energy of 8.79 mega electron volt. Again, if you're seeing that, that is not a milli or whatever, it's mega, okay? Electron volt. Okay, most common binding energy are in mega electron volts. So we also have atomic mass unit. To introduce it now, we have AMU, or atomic mass unit. This is used to describe the mass of an atom, and usually this is the conversion factor that we are using. 1 AMU, or 1 atomic mass unit, is 1.66 times 10 to the negative 24. And if you want to, um, these are still the same, sorry for that. 1 AMU is 1.66 times 10 to the negative 24 grams, or you can do it this way. These are still equivalent. It depends on the conversion factor that you will be using later on for the problem solving. For example here, how many AMUs are in 27 grams of mercury? So we have 27 grams of mercury. 1 AMU of mercury is equal to 1.66 times 10 to the negative 24 grams. So this is equal to 1.63 times 10 to the 25th AMU mercury. Okay, what about an electron volt? It was mentioned here. Oh, sorry, here. So what is an electron volt? An electron volt is another unit of energy that is commonly used in atomic and nuclear physics is the electron volt. It's a common unit of energy that we are using in nuclear chemistry. 1 electron volt is defined as the energy of charge field system gains or loses when a charge of magnitude E, that will be an electron or a proton, is moved through a potential difference of 1 volt. And 1 electron volt is actually 1.6 times 10 to the negative 19 joules. So we'll be using that also in the sample problems. So this is our first sample problem for the radioactive decay of radium. So radium is 22688, and it decays to uh, radon and an alpha particle. So we are asked to get the delta E in kilojoules when 10.2 grams of radium decays. So what do we do? Of course, we have to get the nuclear masses. So if you're not, let's list them so that it'll be easier for us to identify how to use them in the equation. So we have radon. So we're getting the AMU of radon. We go to our nuclear masses table. Let's look for it. So this is radon, I can say here. So radon is, let's highlight the whole thing, 225.977. Let's probably use the whole digits, okay? So radon is equal to 225.9771. Okay, let's just write the whole thing. 225.9771 AMU. Is it AMU? Yeah. Okay. And then we can also look for the mass of radon. Okay, radon, we look for radon on the nuclear mass table. It's, there you go, it's just beside it. So that will be 221.9703. So that's 221.9703. Okay, and then what else? Helium, helium-42. So we'll be using helium-42, not the other heliums, okay? So helium-42 is, I guess we found that a while ago from this part. Helium-42 is 4.00150. Okay, let's just rewrite the whole thing, 4.00150. Okay, and then checking the number of moles, we have 1 mole of radon, one, wait, 1 mole, yeah, 1 mole of Ra, 1 mole of radon, radon, and 1 mole of helium, so no problems when it comes to the number of moles. So what do? We just compute for the mass defect, because for us to be able to compute for the binding energy, we have to get the mass defect. So mass defect is equal to the nuclear masses of products minus the nuclear masses of reactants. Okay, so in this case, this will be our product side, this will be our reactant side. So nothing to convert, since the whole equation runs on 1 molar each. So we just have to add product. We have radon and helium. So this is 4.0015 O plus Rn, that's 221.9703. Then we minus or we subtract radium. The radium is 225.9771. And we're getting here around negative 0.0053 grams per mole. Okay, we can actually say this is also in grams, this is in grams, this is in grams. Okay, so that we don't have to convert. We can assume that. Okay, so that's grams per mole of Ra. Okay, so what do? We're being asked for 10.2 grams of radium. So we can just insert it here. So for the delta M, for 10.2 grams of radium, we will just multiply it. So that's 10.2 grams of radium times 1 mole of radium is equal to 226 grams. And how do I know that? Judging from the mass, okay, the atomic mass of radium, and then we multiply it to, let me just get another sheet, okay, so that it's not cramped up again. For the delta M of 10.2 grams of radium. So delta M is equal to 10.2 grams, and then will be, it's 226 grams of radium per 1 mole. And then we also multiply what we already computed a while ago, that's 0.0053 grams per mole of radium, and the total will be negative 2.39 times 10 to negative 4 grams. Please take note that the negative sign here doesn't indicate a lesser value. It's actually just stating that their reaction is exothermic, or it's giving up energy, or it's losing energy. Okay, so this will be our answer for the first example. Okay, so let's go to the next part. We have another example. What about strontium 90? Okay, let's read the problem. Strontium 90 is a dangerous byproduct of atomic testing because it mimics, oops, wait, am I already done? Or we just, wait, let me just go back. I think that's just mass defect, sorry, we have to go back. So I haven't really solved binding energy. So for binding energy, that's the simpler one. So we'll solve for binding energy by using um, delta M, C squared, or we can use the formula 9 times 10 to the 10 kilojoules per gram, because we just want it in kilojoules, and then of course delta M. This will be the reworked equation wherein we don't have to use a C squared. Okay, so delta E now, but you can always use C squared, 3 times 10 to the 8. So this is 9 times 10 to the 10, and our delta M is negative 2.39 times 10 to the negative 4. So our delta E now here is negative 2.15 times 10 to the 7 kilojoules. So there you go. Sorry for that, we have to go back because I remember from the problem it's looking for delta E. So that will be our delta E for the first example. So let's have another one. Again, okay, now go to strontium 90. Strontium 90 is a dangerous byproduct of atomic testing because it mimics the action of calcium in the body. It decays into two beta emissions to give zirconium 90 with a nuclear mass of 89.8824 AME. Fine. Okay, first we have to write the balanced nuclear equation for the overall decay of strontium 90. We will be computing for the mass defect in grams when 1 mole of strontium 90 decays to zirconium 90. And lastly, we'll be getting the delta E, or how much energy in kilojoules is given off by the decay of 6.5 milligrams of strontium 90. So let's start. Let's probably get another page. So first, of course, we have to identify the reaction. Going back to the um, scenario, it says here it decays into two beta emissions to give zirconium 90. So we'll be expecting two beta, okay, in the product side. So our initial is strontium 90, okay, and this is, if we look at our periodic table, let's get the periodic table. Let's look for strontium. So I haven't really erased. Okay, strontium 90. Let's look for SR. SR. Where is SR? There you go. SR is 38. So we can use strontium 90. This is 38. And then it yields, according to the scenario, it yields two beta emissions. And it yields zirconium 90. And if we check for zirconium, we will look at our periodic table. Our periodic table is listing zirconium as 40. Okay, so that is 40. So that will be the first requirement. We're looking for the balance reaction. Next, of course, to be able to later on get the binding energy, we have to get the mass defect. For mass defect, we'll be using product minus reactant. Okay, so our product will be zirconium and the electron. So we go to our nuclear masses table. What about the electron, ma'am? Do you have? Yes, we also have the mass of an electron. There you go. Let's erase this first so that we can identify it. It's better identifiable. So for the electron, we have, let's use another color. We have this one. It's 0.00055. And then let's look for zirconium. It would be better if you look at or find the masses already before solving the problem. So that's easier later on to substitute them. I can't find them. Okay. That's zirconium and strontium. I can't find them in my table. Where are they? Oops. I don't have zirconium. Okay, I have zinc, but not zirconium. Did I miss it? Zirconium and strontium I have. So strontium is here. I think it's given in the problem. Strontium is 89.8869. I believe if I can't find it here, probably it's in the problem. Let's go back. And the problem says, oh, there you go. Nuclear mass of zirconium is 89.8824. Okay, everything's given. So you just have to get product minus reactant. So product will be um, 2 of the electrons, so that's 0. That's, I think that's 30055. Let's go back. Sorry for only, yeah, 0.0055 plus for zirconium we have 89.8824. Okay, maybe I could do that minus um, strontium. Strontium is 89.8869. So if I compute this, I'll be getting a mass defect of negative 0.0034 grams per mole of strontium 90. Okay. Then, however, we have to check it for 1 gram. So for 1 gram only, then we have 1 gram of strontium. 1 mole is 90 grams. Okay, from the mass number times we have to multiply negative 0.034 grams of per 1 mole of SR. So getting it for a gram, so we have to cancel. There you go, can cancel this one, but we'll still be left with a gram. So canceling that, we are getting negative 3.78 times 10 to the negative 5 grams. Okay, you might as well get the calculators and compute with me. What about delta M for 6.5 grams? You might be wondering where I'm getting those, because here you go, delta M in grams in 1 mole. How much energy is given on the decay by 6.5 grams? So since we already obtained it for 1 gram, then we have to also get it for 6.5 grams. So letter C, let's still use delta M for, sorry for that, 6.5, um, 6.5 of milligrams, okay, not grams. So we can say that that's 6.5 times 10 to the negative 3 grams of SR, and then times 90 grams per mole, and then you can say from our initial it's negative 0.034 grams per mole of SR. This is our computed value. So our answer will be negative 2.456 times 10 to the negative 7 grams. So that's only the mass defect for 6.5 milligrams. You might be wondering how I translated that. So milli, that will be here 10 to the negative 3. And finally, we're getting the binding energy. To get the binding energy, all we have to do is use our solve value for mass defect. So let's get another sheet. Our binding energy now, this is our letter C, is equal to 9 times 10 to the 10 kJ per gram. So I am using this one because our expected binding energy is in kilojoules as given in the initial requirement, and then multiply our mass defect, that's 2.456 times 10 to the negative 7 grams, and of course our final answer then will be negative 2.21 times 10 to the 4th power kilojoules. So just make sure that you'll be solving it depending on the requirement of the problem. For in our problem, we were looking for kilojoules when milligram is given. So be careful with your exponents. So again, milligram, that's negative 3. We're using the factor kJ because our end binding energy should be in kilojoules. Okay, so I guess for this module, let's just recap. Initially, we had the concepts. So always remember, to be able to solve for the binding energy, you start with mass defect. And mass defect is always product minus reactant. Like how we were solving it with our usual chemical reactions. It's always product minus reactant. Product will be on the right side, and then reactants will be your left side. And then after getting the mass defect, that's the time you substitute it to get your binding energy. Okay, for now, just watch out for the next video. Okay, thank you.